Hi, my name is Ansh Chabra, and this is my Physics 2 Lab 5 Magnetic Molasses. To start off, the purpose of the lab was to observe Faraday's law by gathering data on a magnet as it falls through an aluminum tube. The models and fundamental principles of the lab were Faraday's law, the Biot-Savart law, magnetic force on a loop, Newton's second and third law, Ohm's law, and the time derivative of magnetic flux. Some of these models and fundamental principles are shown to the right with these equations given. The preview of the main results of the lab were that the average experimental time of the bar magnet falling down the tube was 1.248 seconds, and the computational model time was 1.168 seconds. The procedure of the lab was to mark the north pole of the magnet, to hold the tube vertically and hold the magnet at the top, and drop the magnet through the tube, getting a video of the magnet and the tube with the entire view, making sure to capture the magnet dropping and leaving the tube, to record the time it took to drop through the tube and repeat this 5 times for 5 trials to calculate the average, and this would be the experimental result. Then you would measure the inner radius, the width of the aluminum, and the total radius, and measure the length of the aluminum roll. The rest of the lab would be the computational model and comparing the results. The main physics ideas on this lab were that the bar magnet falling creates a time-varying magnetic field, which creates an EMF as described by Faraday's law. The current created exerts a force on the bar magnet that opposes the downward movement of the magnet. Newton's second law describes the downward force of the magnet falling based on its mass, and Newton's third law says that the force the bar magnet exerts on the coil is equal to the force the coil exerts on the bar magnet. The initial conditions were that the bar magnet was being dropped through the aluminum tube. The system was the bar magnet and the aluminum tube, while the surroundings were everything else. Assumptions made were that air resistance is negligible, and that gravity and the magnetic force from the aluminum tube were the only forces that acted on the magnet. The data that we used in this lab were that the aluminum tube was the length of 0.467 meters, the width of the aluminum was 0.005 meters, the inner radius was 0.02 meters, the total radius was 0.025 meters. The mu was calculated from lab 3 as 2.645. The magnetic mass was 0.023 kilograms, and the table shown on the right shows the trials of the magnet being dropped through the tube, which would result in the average experimental time of 1.248 seconds. Here's the code of the computational model. This code starts by initializing the variables and the graph, by setting the geometry of the tube in simulation parameters, by creating the tube and the bar magnet, by setting initial conditions, by creating a function to calculate the magnetic field of the bar magnet, and by creating a function to calculate magnetic flux. That's all the code described on this page. On this next page, the code continues by editing forces and variables in the simulation loop to account for gravity, the current in the ring, the magnetic field at each ring, the net force on the magnet, and updating the velocity and position of the magnet. Lastly, the code shows the simulation printing the time and by plotting the graph. The simulation results is shown here, and this is the graph of the velocity versus time of the magnet. The red ring represents the north pole of the magnet and the blue ring represents the south, and that's the time the computational model calculated of the magnet in the tube. The experiment and the model had very similar results, and the model very closely matched the experiment. The possible sources of error were air resistance, because it was negligible in the computational model but not in real life. In our experiment, the magnet was dropped from slightly above the top of the tube, but it should have been dropped from right at the top of the tube, which would lead to more time in our experiment time than it should be, and a last error could be human error when timing. What if the resistivity of the conductor was reduced as close to possible as 0? How would the dynamics of the falling magnet change? Because of Ohm's law, this would create a larger induced current, which would result in a stronger magnetic force against the bar magnet. This would counteract the falling of the magnet and slow the magnet down more, or potentially make it not even move. What if the holes or slots were cut into the tube? How would this affect the ring currents in the model? The current in the tube would be less because it would be disrupted by the cuts, which would result in a weaker magnetic force against the bar magnet, resulting in the magnet falling down the tube quicker. The conclusions were that the lab gave us a better understanding of how Faraday's law could be modeled in real life, and the strength of the induced current is directly proportional to the strength of the magnetic force against the bar magnet, which affects how fast or slow the magnet falls down the tube. Thank you.